In some specific applications in bridge design, the construction of influence line becomes an unavoidable necessity. In this tutorial, I will walk you through a detailed example of the process of constructing an influence line for a negative moment at an interior support of a 3-span continuous beam. This is our example. Here we have an equally spaced 3-span continuous beam, and it's required to construct the influence line for the negative moment at support B. It's very obvious that we are dealing with a prismatic section since EI is constant throughout the length of the beam. The length of each span is L. Although influence line for the negative moment at support B can be found by applying a unit load at several points on the structure and determining what the resulting moment will be for each case, in this tutorial, a more efficient and effective method will be used. Before we get started with the solution, we need to define the sign convention for bending moments. In this example, universal sign convention for bending moments will be used as shown on the bottom right corner of the slide. When the curvature is concave up, the moment will be considered positive, and when the curvature is concave down, the moment will be considered negative. The very first figure shows the negative bending moment at support B. Step 1. Divide the original beam into 3 independent beams and model the continuous ends in the original beam as fixed supports in the independent beams. 1 independent beam for each span. If we are dealing with a 4-span continuous beam, then we have to divide the original beam into 4 independent beams. Step 2. Calculate the fixed end moments for each beam. Beam 1 has 1 fixed end moment. Beam 2 has 2 fixed end moments. And beam 3 has 1 fixed end moment. These fixed end moments can be found almost in all textbooks on structural analysis, mechanics of materials, and codes. Beam 1 represents a case in which a moving load P is traveling between point A and point B. Beam 2 represents a case in which a moving load P is traveling between point B and point C. And beam 3 represents a case in which a moving load P is traveling between point C and point D. Now let's investigate beam 1 thoroughly, because what applies to beam 1 will apply to beam 2 and beam 3. For this particular moment, the moving load P is at distance B from support A and distance A from support B. Both distances A and B are a fraction of L. Therefore, the unit of the term between parentheses will be L squared multiplied by L. L squared can be cancelled out with L squared found in the denominator, resulting a fixed end moment of units load P times variable times the length L. However, in our calculations, the length L has been omitted, and the final results have been multiplied by L. Now we need to distinguish between beam side and joint side. Beam side is the member itself, while joint side is the support. Each member has two ends, near end and far end, near end and far end, near end and far end. Step 3. Place a unit moment on the original beam and determine the internal moments at the supports of the beam. This process should be repeated for the same number of fixed end moments, and the following points should be considered. 1. The moment should be placed on the beam side. Direction of the fixed end moments should be taken into consideration. Case 1 represents beam 1. Case 2 and Case 3 represent beam 2. And Case 4 represents beam 3. Please pay attention to the direction of the applied moment. The applied moments should be in the same direction of the fixed end moments. Although moment distribution method was used to compute the internal moments, the method itself was not addressed thoroughly in this tutorial. The reader can go back to any textbook in structural analysis to refresh his or her memory on this method. The sign convention for moment distribution method is as follows. Clockwise moment on the member is positive, and counterclockwise moment on the member is negative. Now we need to calculate the stiffness factors for all members. The stiffness factor for member AB equals the stiffness factor for member CD, and both are equal to 3I over L. The stiffness factor for member BC is equal to 4EI over L. Next, we need to calculate the distribution factor. The distribution factor for member AB at joint A equals 1. The distribution factors for members BA and BC at joint B are 0.43 and 0.57. The distribution factors for members CB and CD at support C are 0.57 and 0.43. And finally, the distribution factor for member DC at joint D equals 1. Now we are ready to perform the moment distribution analysis. Note that a unit moment of 100 will be used instead of 1 that mentioned earlier in this tutorial. This modification will simplify the calculations of moment distribution analyses. However, the final results of the analyses will be divided by 100. I think that most of us are familiar with the table shown on slide 7. We start with case 1 when a unit moment of 100 at end BA. Note that the unit moment is positive since the fixed end moment on member BA is clockwise. To balance joint B, apply a negative moment of 100 to the joint. The applied moment will be distributed to the connected members in proportion to their distribution factors. We will have a negative 43 and negative 57. Notice that the sum of the moments at joint B is 0. Next, we need to carry over half of the negative 57 to the other side of the member. Now we need to balance joint C. Apply a positive moment of 29.5 to joint C. The applied moment will be distributed to the connected members in proportion to their distribution factors. We will have positive 16.24 and positive 12.25. Notice that the sum of the moments at joint C is equal to 0. Next, we need to carry over half of positive 12.25 to the other side of the member. This iterative process continues until convergence to 0 is achieved. In a similar manner, we can perform the moment distribution analysis when the unit moment of 100 at end BC, CB, and CD. Now let's show the results of the moment distribution analyses graphically. Figure 1 represents a case in which a unit moment is applied at end BA. The resulting end moments are as follows. A positive moment of 0.532 is developed at end BA, therefore the moment should be clockwise on the member. A negative moment of 0.532 is developed at end BC, therefore the moment should be counterclockwise on the member. A negative moment of 0.1332 is developed at end CB, therefore the moment should be counterclockwise on the member. A positive moment of 0.1332 is developed at end CD, therefore the moment should be clockwise on the member. Figure 2 represents a case in which a unit moment is applied at end BC. Figure 3 represents a case in which a unit moment is applied at end CB. And figure 4 represents a case in which a unit moment is applied at end CD. Note that the end moments shown in figures 2, 3, and 4 were constructed in a very similar manner used in figure 1. Please notice that the effect of the applied moment gets smaller as the distance between support B and the point of applied moment increases. What do we call this principle? Before we go to the next slide, I would like to clarify two things. 1. Figures 2 and 3 represent beam 2. 2. The results of the moment distribution analyses, and more specifically the end moments, will be referred to as the coefficients. Before we get started with the final step in our solution, I would like to add the following. In constructing influence lines, the moving load is usually taken as 1. Moreover, in this specific example, we are concerned only with the end moments at the far end of member AB. However, using the end moments at the near end of member BC won't change the results. Step 4. Compute the influence line ordinates. Now we need to construct a table similar to what appear on slide 11. Equation 1 and equation 2 are the equations of fixed end moments. For hinge support, fixed end moment equals 0. Coefficient 1 and coefficient 2 are the end moments for member AB. The following notes should be considered. Fixed end moments follow the universal sign convention for bending moment. The coefficients are positive if they are in the same direction of the universal negative moment. I won't call these rules rather than common sense. The positive sign assigned to the coefficient will neutralize the fixed end moments and prevent the change of direction of the bending moment. Now let's demonstrate the process of computing the influence line ordinates for 6 random points. One, when the unit load is traveling between point A and point B. If A equals 0.8 L and B equals 0.2 L, then the fixed end moments are 0 and negative 0.096. The negative sign indicates that the fixed end moment is in the same direction of the universal negative moment. Please check the universal sign convention for bending moments. When a unit moment was applied at end BA, a moment of 0.532 in the same direction of the universal negative moment was developed at end BA. Now, if one kip foot caused a moment of 0.532 kip foot, what would be the moment if we apply negative 0.096 kip foot? The bending moment at end BA equals 0.532 multiplied by negative 0.096. The result comes up to be negative 0.0511. If A equals 0.7 L and B equals 0.3 L, then the fixed end moments are 0 and negative 0.1365. When a unit moment was applied at end BA, a moment of 0.532 in the same direction of the universal negative moment was developed at end BA. The bending moment at end BA equals negative 0.1365 multiplied by 0.532. The result comes up to be negative 0.0726. Two, when the unit load is traveling between point B and point C. If A equals 0.2 L and B equals 0.8 L, then the fixed end moments are negative 0.128 and negative 0.032. The negative sign indicates that the fixed end moments are in the same direction of the universal negative moment. When a unit moment was applied at end BC, a moment of 0.468 in the same direction of the universal negative moment was developed at end BA. When a unit moment was applied at end CB, a moment of 0.133 in the same direction of the universal negative moment was developed at end BA. Here we need to add the effect of both fixed end moments. The bending moment at end BA equals negative 0.128 multiplied by 0.468 plus negative 0.032 multiplied by 1334. This equation gives us MBA, or the moment at end BA, equals negative 0.0642. If A equals 0.3 L and B equals 0.7 L, then the fixed end moments are negative 0.147 and negative 0.063. When a unit moment was applied at end BA, a moment of 0.468 in the same direction of the universal negative moment was developed at end BA. When a unit moment was applied at end CB, a moment of 0.133 in the same direction of the universal negative moment was developed at end BA. The bending moment at end BA equals negative 0.147 multiplied by 0.468 plus negative 0.063 multiplied by 133. This equation gives us the moment at end BA equals negative 0.0772. 3. When the unit load is traveling between point C and point D. If A equals 0.3 L and B equals 0.7 L, then the fixed end moments are negative 0.1785 and 0. The negative sign indicates that the fixed end moment is in the same direction of the universal negative moment. When a unit moment was applied at end CD, a moment of 0.1334 in the opposite direction of the universal negative moment was developed at end BA. Therefore, a negative sign should be prefixed to the coefficient. The bending moment at end BA equals negative 0.1785 multiplied by negative 0.133. The result comes up to be 0.0237. If A equals 0.4 L and B equals 0.6 L, then the fixed end moments are negative 0.192 and 0. When a unit moment was applied at end CD, a moment of 0.1334 in the opposite direction, again in the opposite direction of the universal negative moment was developed at end BA. Therefore, a negative sign should be prefixed to the coefficient. The bending moment at end BA equals negative 0.192 multiplied by negative 0.133. The result comes up to be 0.0255. Now we can draw the influence line for the negative moment at support B by taking the point values as the x-axis and the corresponding moments as the y-axis. Use simple lines to connect the moments. If you do so, you will get something similar to what we have on slide 12. How do we interpret the graph? If a unit load is traveling between point A and B, the maximum negative moment at support B occurs if we place the unit load at this point. If a unit load is traveling between point B and C, the maximum negative moment at support B occurs if we place the unit load at this point. If a unit load is traveling between point C and D, we no longer have a negative moment at support B. Now suppose we have two HL93 design trucks and HL93 design lane load. Where should we place them to get the maximum negative moment at support B? To get the maximum bending moment, the maximum negative bending moment at support B, place the first truck in this region and place the second truck in this region. Again, to get maximum negative bending moment at support B, place the first truck in this region and the second truck in this region. The lane load should be placed on member AB and BC only. If you apply lane load on member CD, the result will reduce the negative bending moment at B. Any appearance of lane load on member CB will reduce the negative moment at support B. Finally, the influence line ordinates should be multiplied by L. Why? Because we omitted the term L in our calculations. I'm throwing a few problems where you can put what you have learned to use.